hope I can talk with that very nicely. Okay, so this is something that we've never encountered before, what are called reversible reactions. Because normally, when we would see a chemical reaction, we would start with reactants, and they would react and turn into products, okay? Where we just assume that the chemical reactions always go in one direction. They always produce the products. They always go forward with the arrow pointing to the right, okay? We have what are called reversible reactions. That means that, yes, maybe we have the reactants that turn into products, but sometimes the products can turn back into reactants. So that's what makes it reversible, okay? So this reaction is a reversible reaction, bless you, where we've got 2 SO2 gas plus O2 gas makes 2 SO3. This arrow right here is a weird arrow. It's called the equilibrium arrow, okay? When I write it, this is just a picture because the most Word document kind of places don't actually have the equilibrium arrow. When I draw it, you have one arrow pointing to the right and one arrow pointing to the left, okay? And so because you have the arrows in both directions, that shows the forward reaction and the reverse reaction. So the forward reaction is how we would always read it, where we got the 2 SO2 plus the O2 makes the 2 SO3. Okay, that's what I mean by forward reaction, is that it goes from left to right. Okay, now for the reverse reaction, I'm gonna flip it around on you. For the reverse reaction, the product, the SO3, goes back and changes into the other things. So that time, it would be the 2 SO3, and then arrow 2 SO2 plus O2. Okay, so that reverse reaction, remember when we did Hess's law and we would flip things around? It's just like that. It's like flipping, but we don't flip it. Instead, we just have that funky arrow that shows both ways. Okay, so we know that this happens because sometimes you have way too much of one thing, and so we know that it will turn back into the reactants if you got too much product, kind of thing. Okay, the picture I have in your notes, that is a picture describing what's happening here. So in the box at the left, that is only reactant. So if you see, they're all 1S and 2 O's, and then O2s. Okay, so those are all reactants. So then they start to react. So then we get the SO3. So you see the things with the 3 oxygens on them. So we got SO3s now. Well, then maybe all of it turns into SO3. And then that's too much of the SO3s. So then the reverse reaction will happen where it will turn back into the SO2 and the O2 kind of thing. So this going back and forth happens until we reach something that's called equilibrium. Okay, and I know it's a very tiny word at the bottom of the picture, that word equilibrium, but that's what we're trying to achieve here. So now this is what we're going to talk about today and then for our lab tomorrow. Okay, so at the beginning of the reaction, the forward reaction takes place because we only have reactants. When we do chemical reactions for class in here, we only have reactants when we start, okay? But, so initially, the reverse reaction is not going to happen, so it has a rate of 0. But as the forward reaction happens and the products start to form, then the products can start going in reverse. They can start turning back into reactants. So the rate of the reverse reaction will start to grow. And eventually, it starts out slow, but eventually it will reach the same rate as the forward reaction. So whenever this happens, to us, it looks like it's just done because we're not going to see any more change anymore if the rates are equal to each other. And this is where we get chemical equilibrium. when the rate of the forward and the reverse reactions are equal to each other. So I have these two graphs to be helpful with describing what's happening here. And we're going to talk about them now, and then I'll refer back to them in a little bit. Okay, so the first one, the top one, has the, if you notice, it's time for both of them on the x-axis, but on the top one, it's rate, or on yours is the left one, okay? So at time equals 0, so this would be like before the reaction starts, this is showing that the forward rate of reaction is very high, and the reverse rate is at 0. And that's because at the beginning, you only have reactants in the vessel, in the container, okay? But then as the reaction happens, as you lose your products, or as you lose your reactants because you're making the product, the forward rate will go lower because it's not going to have as much to react anymore. And the reverse rate will get higher because it will actually have something to react. Then, over time, the rates get equal to each other. So when the rates are equal to each other, this is where we say equilibrium happens. Starts. I'm going to say that. Okay? Because at equilibrium, the rates are equal to each other. And that's what that graph is trying to show us. Okay? Now, it's hard for people to understand that like things don't just like stop, that there's still continuous movement. It's just something that we can't see anymore. Has anybody ever like been driving on 52 and you go to like pass a car and then all of a sudden that car speeds up, so then you're just like going both together and you have to like, in order to pass them, you have to speed up even more to get in front of them. So if both cars are traveling at the same speed, they're at the same rate. And so there's no change until somebody either speeds up or slows down, okay? So that's what's happening when the rates get equal. It's like the two cars are driving next to each other and nothing's gonna change until somebody changes something else, okay? The rates are equal at equilibrium, right? So that's what that means, of the top one. Now the bottom one, the difference is that it's talking about the amount. Also could be concentration. Concentrations, it could be number of particles, all those kind of things, okay? So at the beginning, at time equals 0, we only have reactants, we got lots of reactants, which makes sense because the forward reaction is the one that's gonna go. And we have 0 products at the beginning, okay? So as the reaction starts, then the reactants get lower because you're losing reactants, because they're reacting and they're turning into products. So that's why the products get bigger. And then eventually, equilibrium doesn't happen here where they cross. Where equilibrium happens is when they get parallel. Okay? So since the rates are equal and there's not going to be any more change that we can see, that means that the equilibrium will be reached when the amounts of reactants and products will no longer change. So that's why we can't see any change, because the amounts stay the same, okay? But it's important to see that the concentrations are not equal. They're just constant, okay? They are parallel. Like you could look for parallel. P-R-A-R-R. Parallel. Is that how you spell it? P-A-R-A-L-L-E-L. Parallel. Okay. So you look at the parallel lines on the graph, and that shows that there's no more change. Okay? So big takeaway from these things. I'm a very visual person. That's why I like to look at these graphs. The biggest takeaway is that the rates are equal to each other, but the concentrations are not. The concentrations are just constant. Okay? So that might be like a true-false statement. Okay. So, when you have unchanging amounts of your reactants and products in the reaction mixture, when you're at equilibrium, since you don't see any more change, it's very common to think that the reaction has just stopped, but it hasn't. the chemical equilibrium is very dynamic. So if we were able to see the individual molecules, we would see that there's still lots of change happening, but we just can't see that with our own eyes. So that's why it looks to us like things have stopped, okay? So at equilibrium, both the forward and the reverse reactions continue, but the rates are equal. Remember, they're like driving along 52 at the same speed. So we don't see any net change. So that's why it looks to us like things have stopped, okay? Now, this is kind of like talking about the second graph that I had pictures of with concentration. So just because the rates are equal, the concentrations are usually not equal, but the concentrations are constant. And how much concentration you have for things will predict the equilibrium position, which is if you have the forward reaction or the reverse reaction, it's more likely to happen. And it has to do with which one is favored. Okay, so if there's a higher concentration of reactants, then that means that the forward reaction is favored. So now we're going to write down two things for this. So this is a modification of the arrow that we had before that was going back and forth. Yeah.
I was just going to say I didn't get
the last blank.
Yeah.
I think it was concentration. Yeah, at the concentration. Okay. So this arrow thing was originally like equal, right? Okay. So if you have more reactants than products, then we show that the top arrow is longer than the bottom arrow to show that the forward reaction would be preferred or favored. If we were looking at a graph, which on your packet you have a graph to analyze, let's say that like the top is going to be the reactants. So starting at the top will be the reactants, and at the bottom will be the products. Okay, because at the beginning we always start with reactants first. So at equilibrium, when they get a constant, when they get parallel, I'm not a very good drawer. That just means that the reactants will have more than the products do. Okay, so that's what that means, is that when you have more reactants than products, then the forward reaction is favored because there's more of the reactants. But if the products are higher, then the reverse reaction is favored. So that's why the bottom line is bigger on that one, to show that it would rather turn back into reactants. And so how the graph might look for there is like we still start with the products and reactants in the same spot, but maybe like there's a bigger dip for the reactants and a bigger growth for the products. So, and since the products are higher here, it's more likely that they're going to turn back into reactants because there's too many, sort of thing. Okay, so this whole like turning back and all these things, once you reach equilibrium, that's the most important thing, is to just remain constant and know that it remains constant. But we're going to talk about also like what happens if you change it up. Like what if you like throw in a stressor or a change to it? Like how does it overcome that sort of thing? Okay. Are we all okay? All right. So I'm gonna keep going forward. Okay. So just it's important to know that under almost all conditions, all reactions are reversible at some extent. You might just have to modify the conditions in order to make it happen how you want it to happen. And normally one set of components is often favored at equilibrium, so the other cannot be detected. And this is why it's just worked out for us all year, that when you have no more reactants detected in a chemical reaction, which is what we do a lot, then we can say that the reaction has gone to completion, or we say that, like, when we did our observation labs, then we said, okay, a reaction happened. But if you didn't witness anything change, then there's no products detected, then we would have called that a no reaction. But what this means is the forward reaction, like there's more products, it's favoring the forward reaction if it goes to completion, and it favors the reverse reaction if it looks like nothing happened, because it all depends on what's present in the vessel at the end. Okay. So now we're going to talk about, so at equilibrium, when we're all constant, right? We're all constant. Now we're going to talk about how do we, like, if something were to happen to change things, how do we overcome that change? Okay. So I'm going to move on. When we disrupt a chemical system at equilibrium, then the system will make adjustments to return back to equilibrium. Okay. So when it's disturbed, it will try to restore the equilibrium. Okay. So when this happens, it's important to note that the equilibrium position might not be the same as it originally was. And that's because the amount of products or reactants may change. So we say that this is called a shift in the equilibrium position. Okay. So the way that we describe these shifts is by using this thing called Le Chatelier's principle. Okay. It's a French guy, Le Chatelier. And the main point is that if a stress or if a change is applied to the system that's already at equilibrium, how will it change so that it can overcome that stress, or it can relieve that stress, or go back to being at equilibrium? Okay, so there's lots of different ways to add stress, so we're going to talk about them all. And we're going to practice this and practice this and practice this, okay? And this is kind of what our lab's about tomorrow too. So the first change that we can do, and this is the one that you just got to get in your head, okay, is changing the amounts, changing the concentrations. So if you were to add or remove a reactant or a product, then it's going to try to make up for the fact that there's now either too much of something or too little of something, and it will shift to reduce that change. So when you are adding something to the system, then you shift away from it. Because when you add something, there's too much of it. It has to use up all that extra stuff, okay? So it will shift away from whatever you added. And so with our problems, we're going to do example 3 in a second. You will have a chemical equation. And so it might say, like, you're adding a reactant. And so then you see, oh, that's on the reactant side. So I have to shift away from the reactant. So I'm going to shift towards the products, okay? So it's all based on the chemical reaction that you have for this problem, all right? Now, if you remove it, if you take it out, that means that there's no longer enough of that. So it will shift to make up for what you took away. So it will shift back towards it. So the two things that I remember, and if you can get these down, it'll really, really help yourself. If you add, there's too much, so you got to shift away. If you remove it, there's too little, so you have to shift towards it. Okay? So add, shift away, remove, shift towards are the best things that you can do to memorize this. Okay. The next one is temperature. We can change the temperature. And this is what we're going to do in our lab tomorrow with our glow sticks. We're going to change temperatures. Okay? So when you change the temperature, the shift is caused based around if it's an exothermic or endothermic process. Okay? So if it's exothermic, the heat was considered a product. And we're going to see this. Remember, we have like our reaction and then like plus heat or plus a number from chapter 17. We're going to see that. I'm probably just going to say the word heat this time because we don't need to know the number. But when you're shifting, so this will be careful, or you just have to be careful of that. Now, for exothermic and endothermic, what I tell you to do, if it shifts left or shifts right, it's important to know that this is for increasing the temperature. So if I were to say lower the temperature, it would be opposite of what it says right here, okay? Some people get mistaken about that. So it's the same process though of add, shift away, remove, shift towards. Because heat will be a reaction in our product and we'll be able to see that, okay? The most difficult of all three changes is when you change the pressure. So when you change the pressure, you have to shift to make the pressure go back, okay? So if you're having gases and there's a change in the pressure, you have to look at the actual reaction to see the number of gases, because you want to shift to the side depending on how many you want, either the side with more molecules or the side with less molecules, okay? So when you have pressure, what you have to do is you first have to count your molecules, okay? And we use the coefficients to add together for a total number of molecules. So for this reaction, I just have this here as an example so we can see how you count. We've got 1 N2 and we've got 3 H2s. So on the reactant side, we have a total of 4 molecules. Everybody see that? Where the 4 comes from? Okay. Then on the product side, we only have one thing. And there's a 2 in front of that, so we've got 2 molecules. So if you ever count and you see that there's the same number of molecules on either side, then there won't be any shift. And the answer would be no shift, no change. But we only count gases, so that's important too. If you ever have a liquid or a solid, don't count it. Okay, now what you do with the shifting, this is important. It's a little bit different than like add, shift away, remove, shift towards, okay? If the problem says that the pressure was increased, so up arrow stands for increased pressure, okay? If the problem says that the pressure was increased, the way that you make up for that is you shift to the side with less molecules. I'll get out of the way in a second. So if the problem says the pressure was increased, that means that there's too much pressure now. So you would shift to the side with less molecules. So in this equation, that would be the product side. So we would shift towards the products because the products have less molecules. And with less molecules, that lowers the pressure back down. Okay? If the problem says that the pressure is decreased, so if the pressure goes down, then you shift to the side with more molecules. So if the pressure goes down, that means there's not enough pressure anymore. So you shift to the side with more molecules so that you can make up for all the pressure that you lost. And that's because there's more particles, means more pressure because of collision theory. Okay? So what we're going to do for all these problems, with example 3 is not a multiple choice question. We're going to give an answer for A, B, C, and D. Okay? And we have all these kind of conditions. So we're going to use our notes. And I am leaning towards, you know how I was really nice and I let you use your chapter 17 notes on the chapter 17 test? If we have a quiz over this, not a test, a quiz, I will let you use your notes too. Okay, so we want to use what I just talked about in the last 3 sections to help us answer this. Okay, so the equation that we have that we're considering is right here. Okay, so A, B, C, and D are 4 different stresses or changes that are going to be thrown at this reaction at equilibrium. Okay, so we're going to have 2 things that we need to write down. One, we're going to determine the shift, and that is going to be like shift left, shift right, no shift, okay? And then after we determine, like left stands for reactants, right stands for products, nothing stands for nothing, okay? After we determine the shift, then we are also going to tell, like, what happens to go back to equilibrium, or like, why did the shift happen? Like, what's the point of shifting left or shifting right, okay? And it all has to do with what the problem talks about, okay? So the first one, A, Cl2 is added, okay? So the first thing you gotta do is you gotta find where the Cl2 is. So it's right here. It's on the product side, okay? So that means that once it's been at equilibrium, then we're just adding a bunch more chlorine gas. So now there's an overabundance of chlorine gas, like there's way too much. So if you look back on page 7, when you change concentrations, it said add equals shift. What did you write down? Add equals shift away. So that means that it says the Cl2 is on the product side, and it's like always different. Like every single problem can be different. But since the Cl2 is a product, then that means that to shift away from it, since it's on the right side, I've got to shift to the left, okay? So the first part for the answer, we're going to say shift left. If you want to write just an L for left, that's fine. I know what you mean. If you want to write out the whole word, that's fine too. I know what you mean. Okay, so we're going to shift left. And why do we have to shift left? And the reason why, for number 2, that's the second thing we have to write down. The reason why we have to shift left is because the Cl2 will react with the PCl3 to turn back into the other thing, to turn back into reactants. The reason why we're shifting is so that we can use up all the extra. So, well, this is what I wrote down. I said use up the extra Cl2. Because if we added Cl2, there's too much Cl2 now, so we got to use it up by shifting the other way. Okay? So that's that one. Now, we're going to skip around if that's okay. Let's do D next, because this is the other one. Like, let's just go in order of the notes. How about that? So D is removing PCl3. So, oh, I didn't want to do that. Sorry. I'll write the answer back down. Shift left. Use up extra Cl2. I don't want to erase the whole link. Okay. This time, the PCl3 is what we're talking about. So, like, every step is like a brand new change to the equilibrium. So, you got to think about it brand new. Okay? So, this time, PCl3 is a product, and it is getting removed. So, when, like, right underneath where it says add shift away, when it's removed, where do you shift? Towards it. So, since it's on the right side, since we're taking it out, we're going to shift back towards it. So it's going to go, this one's going to be, for D, it's going to be a shift right. Because the PCl3 is on the right side. Okay? And why do we do that? We shift to the right because we got to make up for what we lost. We have to make more PCl3 to make up what we had taken away. Okay? So, or I said it like to keep making more PCl3. Making more PCl3. Has anybody ever had that before? Like when you're cooking, you want it to keep going, so you have to take some stuff out so it continues to go. I can't think of an example off the top of my head, but I know that happens. It's just like, that's what we're doing, is that we want the reaction to keep happening. So we got to remove stuff so that it keeps going. It keeps making what we want to collect. Okay, now, C is about the temperature. So now we're just on page 8 now, okay, considering what's due. Now, in the reaction, Let's try not to erase all the lines on the side. Okay. In the reaction, you will see heat written down. In this case, it is a reactant. Okay. So this, does anybody know if it's endo or exo when it's a reactant? It is endothermic when it's a reactant. Okay. So when heat is a reactant or a product, it's going to be treated the same way as if we just did the Cl2 or the PCl3. Okay. So if it says removed, we're going to do the same, like we're going to shift towards it. If it says added or raised, we're going to shift away from it. Same thing with temperature. Temperature and heat are considered the same way, but it's the same thing of add, shift away, remove, shift towards. Okay. So since in this problem we are removing the heat is a reactant, so we're taking the heat out, so we got to get more heat back in. So we are going to shift to the left because it's remove, shift towards, and it's on the left, so we got to shift left. And so the reason why we are shifting left is so that we can get heat back in the system, right? So that we can, I said reabsorb, that sounded smarter to me when I wrote these notes. Reabsorb the heat. Because endothermic really is absorbing heat, right? So that's technically what's happening. Or if you just want to say something like gain the heat back, that would be okay to say that. That would be fine. Okay. Now the last one, which is the most difficult, is pressure. Okay. So with pressure, don't erase all the ink on this side, just erase. Okay. With pressure, first thing we have to do in order to know if anything's going to happen is we count up the gas particles. Don't include heat when you're counting, just don't include liquids, don't include solids, only include gases. Okay. So we've got one PCl5 gas, that's heat. We're not going to think about the heat. So we've got one molecule on the left side, one molecule. And then on the product side, we've got one PCl3 and one Cl2. So add those together and get 2 molecules. Okay. So since it's 1 versus 2, there will be a change because the numbers are not equal. Okay. And so this is where you have to go back to what we wrote down about what's happening. Since the pressure is increased, we said, since it's increased, you're going to shift to the side with the less molecules. So which side has less? The left side does. So because we only have one right here. So since it is increased, shift to the side with less. So we're going to shift left. And why do we shift left? To lower the pressure. That's totally unacceptable. Okay. So we are going to stop here now. All right. For the packet that you picked up today, reactions and equilibrium, we can do through number 4. Okay. 1 and 2 are looking at that graph and talking about like concentrations and all those kind of things. And 3 and 4 are doing this kind of stuff. So it's going to be hard, I know, but I want you to try and do it yourself to see how to do it. And tomorrow for our lab, we are going to just use glow sticks and beakers and water. So we are going to not need to wear our hair up. I'm going to say let's wear closed-toe shoes just so that we don't break a beaker and cut our toe open. But it'll be a nice and easier lab, no math. It's just going to be talking about glow sticks. Okay.